All right, we'll get started. So I just launched the classification competition on Kaggle, and so you will find that module posted as well. So there's now two final project modules on Brew and Learn. You have the regression one, and I think you guys are all there already. I think. Yeah, I think every group now at least has a submission on the regression leaderboard. So that's good. And then the same kind of thing. This time classification, and use the same teams, and you'll set them up in the same way. In that somebody's gonna. You'll click the link. You will all have Kaggle accounts now, so you'll just kind of click the link to join the classification competition. You'll join that. You'll establish your teams, same teams, and then you'll make submissions there. So the classification competition closes exactly 1 week after the regression competition. Okay, so that'll give you. So regression will close a little over a week from today, and then the classification one will close about 2 weeks from today. Okay, and the classification, this one it comes from the 2020 presidential election. The data for the 2024 election is not yet fully available, so I don't know when that information will be become available. But basically, it's county level data. So, it'll be, you will predict based on demographic information. Okay, so if you look at the data set, there's all kinds of, there's a whole bunch of columns, okay? And it'll be, a column regarding the size, the population, what population is male, female, what age, how many there are in the county of a certain age, how many, racial information, all kinds of stuff, education level. Information, okay, and using that information, you will make a prediction, a classification, as far as predicting whether the county voted for Trump or Biden in the 2020 election. Okay, and that is that's there. And let's see. Yeah. So anyway, that's the classification competition, and that is available and posted online. Okay. So today we'll continue kind of working through different aspects of tidy modeling with R, and I think the last kind of chapter we left off was using a grid search to tune hyperparameters, okay? And so this is when your model that you are using to kind of fit and predict, if you want to test out different values. So for example, a threshold value. Do you do a threshold at 1% or 3%, 5%, 7%, and you can set up, kind of a regularly spaced grid. You can set up a grid of randomly spaced values, things like that. And there might be a whole bunch of different kind of parameters, and the grid search will allow you to have this process automated. Okay. There's another process, okay, and we have kind of an iterative search method. And so I'm going to kind of just walk us through the example almost directly from this textbook. But it's I think it's worth kind of taking the time, just because this these methods can produce good results. Okay, so there's two methods in iterative search. There's Bayesian optimization, and there's simulated annealing. Okay, and so we'll take a look at both of these, and we're going to the data here is on kind of cell characteristics and whatnot. Okay, but we're going to do this. Okay, so we're going to use this cell segmentation data, which here, let me go back to that. Okay. Okay, so it's we're looking at kind of this microscopy lab tool for cancer research, and they looked at these kind of human breast cancer cells, and there's different predictors and shapes and things like that, and a lot of these predictors are correlated, but we're going to try to use that to make predictions on the class of the cell here. So you know what? I have not run it on my laptop. I hope this stuff works on my laptop here. But let me. So what we're going to do is we're going to set up a support vector machine model. Okay, and this is going to be used as a classification model. Okay, so let me go ahead and we'll run this. Okay. So what support vector machines try to do is it basically tries to draw kind of like a boundary, like a, I guess the technical term is a hyperplane that's going to separate our different classes here. Okay, and so the simplest kind of support vector machine would be like drawing a straight line. Like if you have data in different classes, you draw a straight line to kind of separate them. But support vector machines, the math behind it allow for what we call different kernels and different parameters that allow you to have not just a straight line, but a more kind of flexible boundary. Okay, and you can have a boundary that is highly flexible and allows for kind of like tight turns and corners. You can have different parameters that allow for small pockets to appear, and so these are different things that can be tuned. Okay, so we're going to do this. Okay, and so the two tuning parameters to optimize are the cost value and this radial basis function parameter called sigma. Okay, and these again will the two parameters. One affects kind of how much penalty there's applied to something falling on the wrong side of the boundary. Okay, and then the other is like how tight the corners can be. Okay, and so if you have they all kind of on the spectrum of bias and variance. You can have the less flexible boundaries, kind of like straight line ones, high bias, lower variance. But then if you have like a very flexible boundary, you're going to have lower bias but high variance. Okay, and so what's the right kind of value to use? That's what we're going to try to tune. And we could just use a grid search, but we're going to find we're going to get better results by using this kind of iterative search method. Okay. The SVM model uses a dot product, and so we're going to center and scale them. And so we're going to do this, okay? And so as we set this up, we have to load up tidy models. Okay, let me also just load up the tidyverse itself. And then we'll tell R to prefer all of our tidy models things, okay? And so our recipe here is just try to predict the class based on all of the other predictors. The Yo-Johnson, that's like, I guess, a normalization kind of scaling thing. So it performs the Yo-Johnson transformation. Let me see if we can have this. Okay, so kind of is similar to Box-Cox transformation, but doesn't require everything to be strictly positive. Okay, and so anyway, we're going to do this, and we're going to scale everything using all numeric predictors. So this is going to be our recipe. Okay, and then as far as our model specification goes, okay, we're going to have our two parameters for SVM RBF. This is our the support vector machine, and RBF stands for radial basis function. Okay, and this allows for kind of these twisty boundaries. Okay, SVM. Let me see, radial basis function. Let me just see if I can show you some images of this. So this is kind of the example here, where you have these different classes, and the radial basis function allows for these different drawn boundaries here. Okay, and actually, we're going to look at this in 102B, but just kind of briefly. Show. Actually, maybe. So these are just examples of when you have a radial basis function kernel. So this is the same kind of classification, but you can see these are the effects. When you have a low gamma, your curve is, very kind of smooth. But then as you increase the gamma to higher values, you can have these kind of very tight turns, okay, as far as the boundary being drawn. So low gamma, so these, we're all keeping the cost, the same parameter here. And so high gamma allows for very kind of tight turns. Low gamma requires the boundary to be fairly smooth. Okay, and then the other thing that you can adjust is the cost. Okay, and so here I'm keeping the gamma preserved at this value of 0.5, so that's going to require everything to be kind of a certain amount of smoothness, and then the cost here is like how bad is a misclassification. A low cost means it's okay to have some observations be misclassified. Like this is the red region, this is the black region, and you can see there's a few dots that are kind of misclassified. As we increase the cost of the misclassification, it's going to try really hard to make sure that these dots don't get misclassified. Okay. And so it starts drawing the boundaries, more tightly. So here at a low cost, it says, okay, these red dots, that's fine. They're misclassified. Okay. At a higher cost, it says, you know what? We really don't want to misclassify those red dots, so we're going to draw the boundary here. And then if I increase the cost even further, it says, I want to avoid misclassifying those red dots, but I also want to avoid misclassifying these black dots over here, right? And so it starts forcing these turns to be kind of really, really tight, okay? Despite, requiring a certain amount of kind of, quote, smoothness. So the gamma over here is kind of how smooth things are, and then the cost is like the penalty applied to how bad a misclassification is. All right, so here is, we're going to keep the gamma at a higher value, so it allows for kind of more flexibility. And as I increase the cost, you can see we can have even tighter turns and kind of these weirder pronounced boundaries for all of these things. Okay, I'm going to look at that later. But anyway, we want to try to figure out what's the appropriate values to use for both the cost and here it's the sigma, but basically that flexibility parameter. Okay, so we specify our support vector machine model. Okay, so we're going to say support vector machine, radial basis function. We're going to make these things tunable parameters. KernLab is one of the available packages or engines used to calculate the thing, and we're going to do a classification. Okay, and then we set up our workflow. Okay, a workflow combines a recipe and a model together, and so this is going to be our support vector machine workflow. So far, I think this is all kind of very, nothing new. Okay. Right now, as far as the parameters, that we are tuning, we have the cost parameter and the RBF sigma. These are the tunable parameters, and right now it says, we're going to check on this transformed log scale going from -10 up to 5, and this is, I guess, going from basically -10 to the minus 100, or 10 to the minus 100, so this very tiny number up to, infinity over here, and then as far as the sigma values, again, looking at these kind of very tiny values up to infinity. And so, how are we going to do that? So what we're going to do is we're going to just kind of update the range a little bit, so it's not so dramatic. And so as far as our tunable parameters, we're going to update the range for this to be from -7 to -1, and so you can see the range here. Why did it not? I guess. All right, maybe it doesn't. Maybe it doesn't show up when I check that. But it's our range is going to be -7 to -1 rather than -10 to 0. Okay, and it says, before discussing the specific details about iterative search and how it works, it just says let's explore the relationship between these different parameters and the area under the ROC curve. So again, ROC, the area under the ROC curve, we want to maximize that. That indicates better classification performance if you have a high area under the ROC curve. So that was from Tuesday's lecture, where we saw kind of just the different classification performance and different kind of so this is the ROC curve, and the performance is measured by the total area under the ROC curve. The maximum is if you have the thing going up to the top corner and you have like a area under the ROC curve of 1, versus if it if you have just a diagonal line and you have an area under the ROC curve of 0.5, that's like random guessing is that kind of performance characteristic. And so we can see how this changes with different kind of values. And so this is the result of using a huge grid. Okay, and so we wouldn't actually do this, but just to kind of illustrate what we're going for, all right, the authors tried out a very, very, very big grid of different values. Okay, so we could actually see the performance of the model under different parameter values. Okay, and so there's kind of just this very there's this huge kind of area where there's not really good performance. Okay, and you do get this tiny little this white area. This is where the performance is good. Okay, and so this required how many? 2,500 candidate values. Okay, so basically I think they tried 50 values this way and 50 values this way, and so after testing out 2,500 locations, we could identify this region as being good, and our best kind of values up here. Okay, whereas but if you don't have the time to do 2,500 operations or these grid searches, like chances are you're not going to find this tiny little thing, right? Like if you just did 25 and you just have kind of like 5 dots, space them out 5 by 5, you might end up picking something kind of over here, but it's going to be really hard to kind of find it. Okay, and so the best performing values are at RBF sigma, I don't know, right around here. It's like, looks like 10 to the minus 3 and something around 32-ish up here. Okay, but this region is hard to find, and you can see the boundaries are kind of sharp. As soon as you crank one up a little bit too high, the performance goes down. As soon as you crank it down a little bit low, the performance goes down, right? So if you have the time to do 2,500 searches, you could detail this out, okay? But we don't want to have to do this tune grid with 2,500 things, okay? But what we will do, okay, so we're going to pretend like we don't know that the answer is this, okay? To kind of just get our things started, we will start with a simple grid search, okay? But this, we're just doing a very, very basic grid search, okay? 4 different values, okay? We're going to have 2 levels for the cost and 2 levels for the sigma, okay? And this is just to kind of set up my initial grid, okay? Just to kind of get some baseline performance here, okay? So that's what this search is going to do, okay? So we are going to do a grid search, okay? We're going to use tune grid, okay? But you can see this grid search, I'm only going to do basically 2 levels. So you can just do kind of like a small grid search. We're not going to do 50 by 50, which would take forever. We're going to just do a small grid search with 2 levels, okay? And so I can see like what my starting grid is, and it just says, okay, there's just 4 values for us to check here, and this is what we're going to do. And then we will do tune grid. So we're going to take our SVM workflow. We call tune grid. We're going to do it on our, do I have my cells fold? I don't have cells fold set up yet. Sorry, I got to go back. I think that's from the previous chapter. cell folds. Where is this? Okay, so let me just set this up over here. Okay, so I have my cell fold set up. Okay, so we're gonna do, we're gonna run TuneGrid using just our very basic grid tuning parameter where there's just 4 levels for us to check, not 2,500. Oh, RSC results. Okay, all right, so actually we need to bring in all of this stuff from the MLP model earlier to RSC, where is this? My metric RSC results, metric set, sorry. I need to just establish a few more. So, all right, hopefully this works now. All right, so it's doing all models failed. Uh-oh. None of the variables in the recipe are present in the supplied train set case. Okay, let me just try this all again. Okay, all right, I think it's working now. So I had to rerun it because when I used the data, I had it didn't run this operation earlier. Okay, so here it's doing its TuneGrid, and it's just doing it just for the small grid where there's four levels to check, and it's still taking a while. So, you know, doing it for 2,500 would have been extremely painful. So we wouldn't, so we're gonna let it run. I hope it's working okay. Sometimes it hangs. But anyway, we get, we get these results, and we can see, just kind of like the different, still running here, but when they run it, you look at the results here, and we have 0.864, 0.863, 0.863, 0.866. We're not getting, like, as far as these 4 values go, it's kind of just like probably just bland results that are all kind of very similar, and we haven't really found the breakthrough right there. So so what we're going to do is we're going to try one of these iterative search methods. Okay. And so one of them is Bayesian optimization, okay, and it takes basically the current results, all right, and says it tries to make a predictive model to suggest the tuning parameter values, okay, and it then tries the suggested parameter combination is then resampled. Those results are then used, and then they set up another predictive model. And basically, it's like based on the things that you have now, it says, okay, basically using these 4 values and these results here, it's trying to predict, come up with some kind of model that says, all right, it's almost like setting up, like we're having like a model built on top of this data here, okay? And it's like, if this is the response, okay, and these are your predictors, what's gonna be like the best combination that's going to create an even lower thing, right? And so then it tries out a new value, and then it plugs that in, all right? And so now it has another data point, and it says, okay, now we have more information, and now I have 5 data points, and I'm going to create another model, right? It's kind of almost like you're doing it's not linear regression, but it's almost like you're doing linear regression where you say okay, here's new observations. Okay, now with that, this is as I change this variable and this variable, what combination is going to give me an even lower value, and it tries on another value, and it does kind of this iterative thing where it just says, all right, here we're going to start off with 4 locations. We'll do a 5th based on that. I think I should try out this. Here's a 5th location. Now I reevaluate the model. Based on that, let's try another location. And it does this kind of iterative thing, okay? And so, again, it's not linear regression. It's we call this a Gaussian process model, okay? So it says, when using Bayesian optimization, the primary concerns are how to create the model, how to select the parameters recommended by that model. And so we have this Gaussian process model. And so right now, we have 4 observations to start off with, right? We started off with this very basic grid, okay? And these are our results right now. Okay, so it's done. Okay, so these are our results right now. And so based on these predictors and this thing, let's come up with another thing, okay? And so, it gets into the math behind the Gaussian process model as far as how it's going to pick the next thing. You don't have to worry too much about it, okay? But I guess, all right. So okay, it's these techniques in spatial statistics, and they can derive in all kinds of different ways. And I don't know what do I need to say. But basically, we're using these 4 observations to kind of say okay, I think what I need to do is set my parameters to be a certain way, and we're going to maybe get an even lower ROC. Okay. All right. So, and then when we do that, we have this kind of iterative function, right? And so it says, once the Gaussian process is fit to the current data, how is it used? Our goal is to then choose the next tuning parameter that's going to likely have better results, okay? And says, one approach to do this is to create a large candidate space and then make mean and variance predictions there. And so anyway, this method, we use what's called an acquisition function, okay? And we have these different concepts of exploration and exploitation, okay? So exploration says, as you go searching, right, try searching areas where there aren't very many other observations, right? And go explore uncharted things just in case you find something that's good, okay? And then exploitation is kind of just all right, based on the ones you have seen, right, then exploit or find the best values around there, okay? And so this is just kind of a silly thing where it's all right, if you were trying to find the best value of this, where should you go? And if this is where you started, this might be what your estimate is, but really, the best values up there, and kind of the this is what we have. And so this is just saying all right, these are areas where you should go explore, okay? All right, so anyway, all to say, what we're going to do is we're going to use this tune Bayes function, okay? And so the tune Bayes function is going to kind of take this as inputs based on what it sees here, all right? And the outputs here, it's going to try tuning, adding additional things here, okay? And so we have a bunch of kind of control options here, okay, as far as how tune Bayes goes. But basically, you start off to do tune Bayes, you start off with a tune grid with just kind of some very kind of basic initial values, okay? So you need to have kind of a starting place. So we have these 4 initial values, and we put that into Tune Bayes as our initial things, okay? The thing that we're measuring is the area under the curve, ROC area under the curve here. Okay, that's our metric set. We're doing it on our vfold cross-validation set up as cell folds. The parameters are the cost and RBF sigma thing, okay? So basically, to use Tune Bayes, you just start off, you have like your initial kind of 4 values there, and then you say, all right, go ahead and run 25 iterations based on this, all right? And what it's gonna do is it's gonna try new values, okay, to try to figure this out. It's going to take a while, okay? So Gaussian process model, and it says, we're going to try this, and it's doing a bunch of this. Okay, so we're going to let it run, all right? And then, so right now, when it started, its best model was, its best model was this one, okay? And so based on that, where's it? Sorry, yeah, for the area under the curve, it was 0.8659, and then it says, okay, we're going to try to do this. All right, it says the first iteration failed to improve it at 0.8631. I don't know if my computer comes with the same thing. All right, so it's trying each of these things out. Okay, so it's doing each of these things. Is it printing out results here? Estimating performance, it just says estimating performance. Okay, so we can't really see until the end, but it says that it tries out a whole bunch of these things, and they score a bunch of these things, and then they do improvements, or they attempt improvements. Okay, and it says according to this, we ran 25 iterations. Okay. And, with every attempt, it doesn't always find something that improves, okay? So iteration 1, iteration 2 didn't improve, but apparently when the book authors ran it, it improved on iterations 3, 4, 5, and 6, did not improve iteration 7, did improve iteration 8, did not improve iteration 9, 10, 11, 12, or so on. And it kind of keeps searching, and then eventually it did improve iteration 24, did not improve iteration 25, and after iteration 24, the best performance it had was 0.8986. And so you can see, the steps at where it did improve, and these are the parameters that it went for. Cost of 31.8 and a sigma parameter of 0.0016. Okay, and I'm not sure if my thing is still running. I'm not sure. Yeah. No. Okay. So anyway, it does these 25 iterations, each one trying to generate different things, picking something, and so at the different kind of iterations, so some of the iterations it did not improve, right? So no real improvement, iterations 1, 2, but an improvement on iteration 3, 4, 5, and 6. Not an iteration 7, improvement on iteration 8. Okay, no improvement here until we get to, I think, iteration 15. No, 13. And then after 13, nothing until we hit all the way over here, where it doesn't even look like we're improving that much, right? And we tried out a whole bunch of these, and these ones did not improve at all. This was our initial 4 values that we tried out were here, okay? And it said, okay, based on this, let's try out a new location, and it suggested we should try out this location and this location. It tried it, and then so this is an animation of like where it thinks it should try out, okay, based on its results, right? So it first started off at these 4, and then it said, okay, let's try here. It didn't get better, so it tried over there, and then it did get improvements, so it went over here, okay, and then it did get an improvement, so it tried. So it's just trying out these different locations as far as you know, where it goes next, and eventually, as it's kind of searching, it says, all right, we're gonna try out these different locations. It tries out over here. It's no good over here, okay? So then it says, okay, well, we'll try over here. It's no good. So it's really kind of convinced that this is going to be the best location to kind of keep seeking, right? And based on these are the different locations it has tried, these different black dots that it has tried, and you know, where does it think it's going to be good? And so we can see that as it tries out different locations and sees like different performance, you know, the results of this thing as far as what the Gaussian process model predicts, this is actually kind of reasonable, okay? This is kind of a reasonable thing because, again, the true result, which was found by doing, you know, 2,500 locations, you know, found this to be kind of the graph there. And this is based on the Gaussian process. This is what it thinks after 25 iterative iterations, right? So it starts off with these 4, tries out different locations based on what it gets. It fills in the blanks and says, okay, this is what we have here, okay? And so let's see if it's done. No, it's still running. Okay, but anyway. This is the result. After, you know, 25 searches, you know, it found something with pretty decent performance, okay, at pretty close to kind of the optimal location. So that's one method for iterative search, is this Bayesian tuning grid, okay, or not tuning grid, but I guess Bayesian search, okay. The other method, as far as doing an iterative search, is simulated annealing, okay. I just want, I don't know how many of these things. Let me see. How close are we to being done? 1 iteration, 2 iterations, 3 iterations, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, all right. I think we're at around 17 out of 25. Okay, so simulated annealing, this, the name comes from like metallurgy. And so in the annealing process in metallurgy, it's kind of this changing the temperature of, I guess annealing your metals. So like to improve the elasticity, like how much your metal can bend, but also how hard it is. I guess you can kind of like put it in the oven type of thing, and if you have different temperatures, higher temperatures and lower temperatures, and I don't know, I'm not a materials guy, so I don't know these things, but apparently you don't want to just, I don't know what the right word is, cure the metal in the oven at the same temperature the whole time. You want to kind of vary the temperature. And I think you start off with a high temperature and bring it down cooler slowly or something. I don't know. But it's kind of this idea that in the beginning you have like these, you search kind of big, and then your search gets, so you're starting off with kind of like these big jumps, and then as you kind of get better things, you can kind of fine tune your search. Okay, so it says it's simulating annealing is a general nonlinear search routine inspired by the process in which metal cools. It's a global search method, okay, that can navigate a bunch of different types of search landscapes, including discontinuous functions, and unlike gradient-based ones, it can reassess previous solutions. All right, so it starts with, okay, like everything else, starts with an initial value, embarks on a controlled random walk through the parameter space, and each kind of new location is going to be a small perturbation of the previous value that keeps the new point within the local neighborhood. So, you start your search here, and it says, okay, we're going to just kind of pick a new random value that's not too far away, okay? Candidate point is resampled. You get, so you pick this location over here, you check its performance. If this is better, okay, this is going to start the new best, and the process continues. If this new location is worse, okay, it might use this to try another thing, or it might keep the original one, right? So this depends on so the likelihood of accepting a bad results is going to decrease as the performance becomes worse. So if you try out this new location and it's like much worse, you're going to say, all right, we're definitely not going to take it. But if you try out a new location and it's only a little bit worse, you'll say, well, maybe it's worth keeping, all right? And we'll keep kind of searching, right? So it's with a gradient-based thing, it's kind of like every step has to be an improvement. And if you take a step and it's not an improvement, you're like that's like a dead end, okay? With this, it says like, okay, not every single step has to be an improvement, right? You take a step, if it's like way worse, okay, fine, we're not going to go that way. But if it's only a tiny bit worse, or if it's kind of comparable, why don't you just try it out, okay? And that's how it goes, right? So a slightly worse result has a better chance of acceptance than one with a large drop in performance, okay? And then the other factor is the number of search iterations, okay? So simulated annealing wants to accept fewer suboptimal values as the search proceeds. So in the beginning, you're more willing to take a step that has worse performance, okay? You're willing to take kind of these more riskier steps. But then as the search goes on, and as you have more and more iterations, you're going to say, okay, by now every step we take should be an improvement, okay? And we're rarely going to accept, new locations that are a little bit worse, okay? All right, so it says the probability of accepting a suboptimal parameter, so basically parameters that are not as good as the previous iteration, okay, is going to be, the product of all of these things, okay? The iteration number and basically the percent difference between the new and old values, okay, where things are going worse, and then some other kind of constant there, all right? And so, so you can see at these different kind of coefficients, okay, at different iterations, this is what we have. So when you have, in the beginning, you're willing to accept, a loss of anywhere from, 0 to 10%. These are all like, you pick a new location and it's 10% worse, you're willing to accept it, okay? But as it goes on, okay, by like iteration 40, okay, you are not willing to accept a 10% loss, okay? You might be willing to accept a 2% loss or a 3% loss, but not a 10% loss, okay, if the performance goes down 10%, okay? These different coefficients control like how sharp the drop-off is, okay? So if you have a coefficient of 0.01, it says, at iteration 20, maybe you'll accept a 5% loss, okay? But at a coefficient of 0.03 at iteration 20, you're very unlikely to accept a 5% loss, okay? So coefficient 0.03 basically says, in the beginning, I'm willing to accept some losses, but as time goes on, I really don't want to accept, worse parameters. Whereas coefficient 0.01 says, I'm willing to go a little bit longer, or I'm willing to accept, slightly worse parameters, okay? And so these are different values that you can, this is the cooling coefficient, okay? I guess how rapidly, so I guess high temperature is kind of analogous to accepting slightly worse performance, and then as it kind of cools down, you're not willing to take these risks, okay? And so I guess this is part of one of your controls that you can adjust in the fine-tuning in the simulated annealing, okay? So this process continues for a certain number of iterations, but it can halt if no globally best result occurs within a predetermined number of iterations. And it can also be helpful to have a restart threshold, okay? If there's a string of failures, it just revisits the last globally best parameter and starts anew, okay? Anyway, let's check back on this. Oh, okay, all right. So going back to our Bayesian search, let's see how our results went. And wait, how do we check our best parameters? I forget. Show best. That's what we want. Show best. SVM Bayesian optimization. Okay, and it says, yeah, our best. So when we did our search, our best came at iteration 19 with a cost of this and a gamma of that. So our values are a little bit different, but we are getting similar values for the mean. As far as the area under the curve, 0.899, we're getting something similar to 0.899 there. Let me see. Auto plot. Let's see what our auto plot looks like. So iteration 19 was our best one. So yeah, in the beginning, we got improvements after iteration 1, 2, 3. No improvement there. 9, 10, 11 was our next best. We tried a whole bunch. None really came out well. 19 was the best. We tried more, and then didn't get much improvement. But, so we're not too far off. So our optimal parameters is at 24.1, 0.00185. I'm just kind of curious. Going back to the huge grid. So 24.1, this is on some weird scale. So 24.1 is probably over here, and 0.00185, yeah, I guess probably somewhere similar over here. Not the exact same location, but also not too far off. Okay. All right, going back to simulated annealing. To run simulated annealing, we'll run this tune simulated anneal, okay? This is kind of the neighborhood in which it's searching, and so this is just like where it's willing to kind of search, and then it picks a location, and so it moves up here, and then it picks another location and moves up there. It searches over here, and it moves around, okay? And it picks over here, and so on and so forth, okay? All right. The syntax for simulated annealing is identical to using basically tune Bayes, which is very similar. We have control simulated anneal for some of the different options, okay? And the different options you have is basically no improvement integer that will stop the search if no global best is discovered within a certain number of iterations. So it's like if you try out 5 iterations and you get no improvement, should we just stop there? Okay. So it says accepted suboptimal or discarded parameters are counted as no improvement, right? So let's say at iteration 19, that was our best, and then we searched iteration 20 and 21 and 22 and 23 and 24, and we're not getting improvement. We might accept suboptimal ones to continue our search, but this still counts as no improvement until we get something better than like 19, okay? When do we restart? Okay, how far back, how big of a radius do we do to search, and so on and so forth, okay? So we will run this simulated annealing, and we're gonna just say if we have no improvement 10, okay, and so this is what it goes. And this might take forever on my computer to run. Okay, but we'll see. Control simulated. Why is this not? Oh, fine tune. Okay, I have to. Sorry. I do most of my prep on my desktop at home, and then I come to use my laptop, and it doesn't have the same packages, so. Okay, so now we should work. Okay. All right, so same thing, okay? We're running, we get our estimate of performance using v-fold cross-validation. Our metric is the ROC area under the curve. We also have kind of our initial setup here, okay, which was the where we did the tune grid, kind of our 4 initial values, okay, and then we're going to run our search from there. Simulating annealing, so I think this is going to take a while. So initial best 0.8659, and it's trying to. Okay, this is going to take forever. All right, but anyway, we let that run. And it finds something similar, 0.8985 after several iterations. Okay, so after 50 iterations, this is where it ends up. Okay, and so again, we start off here, and it's searching around. Okay, and we're getting some improvement, no real improvement. So kind of. Restarts, and then does find some improvements, and so on and so forth. Okay, and as it's going, it's just trying out these different values. Okay, so the Bayesian iterative search uses a Gaussian process to kind of guess where it should go next. Okay, whereas simulated annealing just uses a random circle of points. Okay, it just says, okay, you're right here. Let's just try another location, and then let's just try another location. Let's just try another location. So it just kind of looks at a tight circle and picks one of them. Okay, hoping to find something here. Okay, so here it just says, all right, this one was the best one, and then it picks a random location not too far away, and it accepted it and ended up over here. And so this is simulating annealing. It's just trying to pick just random locations within some kind of circle. Okay, so it accepts the suboptimal, and let's see. this one is better. It's kind of going in the wrong direction. Let's see. It's like watching an ant crawl, right? And you're like, so after a certain number of iterations, it kind of gave up that path, and so it restarted, okay? And it's just kind of like walking around, and you're just saying like, oh, please, the better location's over there, okay? But again, we don't actually know where the better location is, right? We only have this answer because the authors of the book did a very, very, very extensive grid search with 2,500 locations. But in general, we don't actually know what it looks like, and so we're just kind of walking around blind, and we're hoping, and then so just kind of by luck, we ended up over here, and then we tried another location, we ended up over here, and we say, oh, this is great, okay? And then we start looking around, and again, now we're getting bad results, okay? So we're trying these things, and we say, okay, well, that's better, but this is no good, this is no good, this is no good, and as the process runs longer, you're less willing to accept worse results. So, we kind of restart from the best location, and we kind of keep searching. And so basically, we're going to kind of end up around here because pretty much all of these other locations that we're testing out don't look that great, okay? But that's basically what simulated annealing does. So the Bayesian iterative search often works great if, as long as this Gaussian process, which is a lot of times is a reasonable process to assume, okay, for your parameters apply. Okay, so anyway, this is the iterative search, and it is often a pretty effective way as far as fine-tuning your hyperparameters, okay? So the grid search is great, okay, but it's going to take a really long time if you want to check out a whole bunch of locations. And depending on your model, there might be just a slim location of optimal parameters, okay? So, you generally, we would recommend doing the iterative search. You start off with a grid search with just a few locations, kind of like 4 locations, and then you transition to an iterative search using those 4 grid locations as a starting place, and then either doing simulated annealing or Bayesian optimization, okay, from there. And then, as you do this, you're going to want to have to screen a whole bunch of these different models. And so I have a few slides here on workflow sets. Where did I put it? Okay. So, as far as workflow sets go, there are, you might want to try out a whole bunch of different workflows and things like that. Okay. Oh, this was just a little tip regarding the election data. Okay. So one of the things you can do in your recipes is you can use step mutate. So this is kind of, I guess, just a side note here. Step mutate to kind of create new variables. So, for example, in the classification competition with the election data, you have these different kind of variables, okay? And so you might, here I think this one was a mistake. I used to have this it used to be predict the percentage that voted for Biden, but now it's just a classification thing, okay? But anyway, you could have, you can create new variables, for example, like, what is the percentage of voters in the county that are male or something like that, okay? And you can just kind of take like the total male population, divide by the total population, okay? And then there's other variables like how many people are between ages 20 and 24, and then another variable for how many people are in between ages 25 and 34. And, as you're thinking, you might say, well, you know what? It might make sense to kind of put them together, okay? So you can create like a new variable for like the total number of people that are between ages 20 and 34, right? And so you just kind of add these two numbers together. Or you can use like what's percentage of people are between ages 20 and 34. And you can kind of take, the total number divided by the total population. And so you can kind of create these additional variables based on other variables that you might find to be useful, right? So you have in the competition, there's a whole bunch of these different variables, okay? And it might be you might have too many, okay? Some of there's a lot of variables, and it might not be useful to have it kind of broken down at this kind of level, okay? So this is for some of this race information, okay, it splits it out by Asian, Indian, Chinese, Filipino, Japanese, Korean, Vietnamese, other Asian, and things like that. And you might say, I don't need to have it all broken out here, okay? You might want to kind of put some of them together, and that might actually improve your model performance, right? So these are just some different ideas and different things to kind of test out. And so you have a whole bunch of these different variables. Should you keep them all separate? Maybe collapse some of these, do we throw away any of the variables? I don't know, right? So these are just different kind of things that you can try out, regarding, education. Like, does it make sense to group together bachelor's and graduate degrees or things like that? So just different ideas, and you can do that using step mutate. That simulated annealing search is still going. Okay, so that's there. We'll bring in this other data set on Chicago ridership. Okay, this is just another. Okay, well, I'll just let that run, and we'll just look at this. Okay, and so this is the Chicago kind of public transit system, and there's different stations. Okay, and you have these kind of different ridership numbers, like how many people rode public transit from this station. Okay, total ridership, how many got on at this station or that station, all these different station locations, okay? And so, as always, we will do a kind of a train test split, okay, on our data, and then we're going to try out a whole bunch of models. And so we're going to set up what's called a workflow set, okay? So a workflow, as we've established, pairs a recipe along with a model, okay? And so you might have different recipes that you want to try out. You might have different models that you want to try out, okay? And so a workflow set will put a bunch of workflows together, okay? So you might want to try different types of models, different pre-processing methods. So you might say like, okay, here's a recipe where I've created this variable. Here's a different recipe where I created other variables, right? So you might want to try out, all right, here's one recipe where I decided to combine these different groups together. And here's another recipe where I didn't do that. And here's another recipe where I calculated these percentages and these relative things. So maybe it's not, the age, but maybe maybe it's not the percentage, in this age group, but maybe it's like the ratio. In this county, there's more people between ages 20 and 34 than there are people over the age of 65. Okay, and here's a county where that ratio is flipped around, and maybe that's the predictor, or maybe not, right? And so you have these different kind of recipes where you're trying out different kind of predictors and new features and things like that. You have different models. You got your SVM, your random forest, things like that. Okay, and so workflow sets is going to kind of create sets of workflows and allows you to kind of test them across that. Okay, so for the Chicago train ridership data has a bunch of numeric predictors that are highly correlated, and there's a few kind of approaches that we can try for handling this issue of having highly correlated things. So one is we can do a feature filter to remove redundant predictors. We can apply principal component analysis to find uncorrelated predictors to decorrelate the data, or use a regularized model to make estimation less sensitive to correlated predictors. Okay, so one recipe is predict ridership based on all the other things, and we're going to create different features. Okay, so one is take the date variable and turn it into an actual date column. Okay, and then there is a step holiday that will figure out if a day was a holiday or not. Okay, so this is especially useful if you have like business related data, which as far as your projects go, we don't have that. But in this case, knowing like if someday was Labor Day, right? And you go, oh, why are the numbers so different? Like it looks like a Monday, which is normally high, but this one is different. And if you find out, oh, that was actually a holiday, we have that. Okay. We don't want the date itself to be a predictor. Okay. So we're going to set that up as an ID column, and then we're going to make dummy variables out of our categorical variables, all nominal. Okay. Step ZV is get rid of any column that has the same value. Okay, so if there's zero variance down that column, just get rid of that column, and then we'll normalize. So any center and scale. Okay, so that's going to be our basic recipe, and then we're going to try a few different other steps. So starting with that base recipe, we can say filter out. Okay, so step core just gets rid of redundant predictors. So it's going to say, all right, oh, these variables are correlated. It's just going to keep one of them and then throw away the other variables. Okay, and it's if the correlation is above a certain threshold. So you might set a correlation of 0.9 or 95% or 99% correlation or 98% correlation, and we'll make that a tunable parameter. So we'll run either like a grid search or Bayesian optimization or something to figure out what threshold parameter to use here. Okay, so this is going to be one recipe that we can try. This is the filtering recipe. Here, instead of filtering and getting rid of correlated predictors, we can run PCA. So PCA is a technique to create uncorrelated predictors out of things. So we'll run step PCA on all of our station variables. Okay, number of components to try out. So we'll make that a tunable parameter. Okay, and then again we'll normalize all of this. So this is going to be another recipe that we can try out, and then we'll have a few different models. Okay, so we have the filtering recipe, the PCA recipe, and then as far as different models, okay, we can create a linear regression model where we will have different regularization things. So you can run lasso or ridge regression, and mixture is going to be a number between 0 and 1. 1 is, I think 0 will make it all lasso, 1 will make it all ridge regression, and 0.5 is somewhere in between. And then how much penalty to that complexity to apply, that's going to show up here, okay? Cart is to make a decision tree, okay? And we have the cost complexity parameter that we talked about when we made decision trees. You know, the minimum number of observations before you split the tree, okay? And so that's another kind of model. We can also do k-nearest neighbors, okay? K-nearest neighbors, how many neighbors do we want? Okay, we're going to try tuning that. Do we want a weight function? We can try tuning that. So we have 3 different models to try out, okay? And so what we're going to do is we are going to create a workflow set, okay? And we're going to take each of our recipes. We have the base recipe, the filtering recipe, and the PCA recipe. So we have 3 recipes, and we have 3 models, okay? And we're going to create a cross between all of them, okay? So we're going to have a total of 9 workflows to try out, okay? So our preprocessors, we've got 3 recipes, the simple, which is our base recipe, the filter recipe, and the PCA recipe, okay? And then as far as our models go, we have GLMNet, which is going to do the lasso or ridge. We have CART, which is going to do a regression tree, and KNN, which will do k-nearest neighbors, okay? And when we call cross equals true, it's going to do all 3 of these crossed with all 3 of these. So we're going to have a total of 9 combinations here. And this is going to be our Chicago models, which will be our workflow set. Okay, so when you look at the names of the Chicago models, it basically takes the names here, puts an underscore, and pairs it with each here. So it takes a preprocessor along with the model. So we have simple GLMNet, simple CART, simple KNN, filter GLMNet, filter CART, filter KNN, PCA GLMNet, PCA CART, PCA KNN. Okay, so we have 9 models here. Right now we haven't tried fitting any of them to anything, so it's just everything over here. All of our options, all our results right now are just empty. Okay. One thing is that with GLMNet, it doesn't quite make sense to use PCA or filtering, so we're going to get rid of Model 7 and Model 4 here. So we're actually going to just have 7. All right, so anti-join is a way to kind of just says, hey, get rid of anything here. And so we're going to get rid of PCA GLMNet and filter GLMNet, okay? So now we just have 7 models for us to check out, okay? Simple this, that, and that, okay? So we have these things, okay? So no PCA GLMNet and no filter GLMNet, but we do have CART and KNN there. All right, we'll set up our k-fold cross-validation there. And then now we're going to do this, all right? And then so as far as this goes, I'm just going to do, I'm not going to bother doing Bayesian optimization at this point. I'm just going to do kind of a grid search with 10. So I'm going to just call tune grid here. I could call tune Bayes. I could call tune simulated annealing, and it would just take an even longer time. Okay, you know, if you want to do that, you'd have to probably start off with a small grid, maybe 4 values, 5 values there. Put that in as kind of your initial set, and then you would do tune Bayes there. Okay, so you know that's possible. I didn't do that. I just ran tune grid here. And so with our workflow set, okay, all right, we're going to take all of our 7 models here, and I call workflow map. And with workflow map, I run whatever tuning system I want. So I can do Tune Grid. If I wanted to, I could also do Tune Bayes or whatever. I guess I could take Tune Grid here, run the workflow map, and then take those results and then do Tune Bayes if I wanted to or something, okay? We run it on our vfold cross-validation. We have all of our metrics. This one is just going to be the mean absolute error as far as our metric set goes. Just one metric here. And then I say verbose true, and it says, okay, it's tuning for GLMNet, simple GLMNet, simple CART, simple KNN, so on and so forth. It does all of these things. Okay, and now it finishes. So after this, it takes, again, everything kind of takes a while, and you'll have experience with this as you do your competitions and predictions. Okay, and so we get our different models, and we can kind of take a look at the results here. All right, so the results are all showing up in here, and we can expand that. So here's just the auto plot, okay, as far as the mean absolute errors go, and so we can see, you know, these different models seem to have you know, different values, and it looks like these ones, as far as the best, you know, what was the best nearest neighbor model, and we had the 3 recipes. The best nearest neighbor model is like down here and here. Unfortunately, the plots we can't really see, but it looks like our best one was our linear regression model. So we can rank our results and see, like, all right, which one seemed to have the lowest mean absolute error. And it looks like the simple GLMNet has the best performance of the different things we tried out. We have, next up we have PCA CART, simple CART, and so on and so forth. And we can see kind of these different results here. And so that's kind of an exploration. You know, once you have this, you can also continue trying, and you can do, you know, further tuning. So, you know, here I just did Tune Grid. I didn't do Tune Bayes or Tune Simulated Annealing Tune SA. You can try any of those to try to find an even more optimal parameter set. Okay, kind of a lot of stuff there regarding this. My hope is that it will be helpful as you work on your competitions, as on your projects. You know, and right now I'm not assigning homework. Okay, that's it. No more homework assignments. This is really, it's going to come down to your projects, and there's a temptation to like not do anything, right? It's easy when there's no pressure to not do anything, but I do think you'll get a lot more out of the course if you do like actually try things out, try new and I don't know, adventurous things. Okay, a lot of it is you are going to have to read the documentation yourself to learn how to use something you've never used before. Okay, my hope is, you know, these lectures are just giving you kind of a starting point, and you will do the exploration and try out an experimentation yourself with these different things. Okay, so the documentation is a great resource, and yeah, look at that. The Tidy Modeling with R textbook is also really good as far as kind of walking you through and explaining the thought process behind a lot of these things. But as you work, I want you to do the exploration yourself, and I think you'll get. My hope is you'll get a lot out of it, right? So everything you explore, not everything you explore is going to work out, but that's part of the journey, okay? try out different things. This was a very kind of low stakes environment. You're just predicting things for a class, right? But the idea is it'll prepare you in case you do have something important that you do want to predict and things like that. So, okay, we'll wrap things up here. Have a great weekend, holiday weekend. But I don't know, we don't meet Mondays anyway, so we'll see you on Tuesday then. Okay, all right, see you then.